Yes.
Thank you. Thank you for confirming. So till now, what we have discussed is first one is the basic terminology. First day, AIML, DL. Otherwise, let me type in the Excel sheet. That is better for this one at least. Yeah, basic terminology. That is AIML, DL, Chennai. And then next, what we have discussed is about the uh, learning paradigms. Yesterday we have discussed, and then how does the machines learn? We have discussed that point as well, and what is it meant by training and the training methodology that we started yesterday. That is what we have done, right? So just as a repetition, like basic terminology, what is AI? Like building the machines that can think intelligently or that can behave intelligently, that can take the action in independent way. That is what is AI is. And in machine learning, we deal with uh, only structured data, and using algorithms, we try to build the intelligent systems. And in deep learning, deep learning is what to say, subset or subdomain of machine learning, where we use very specific architecture that is loosely inspired. The term loosely I am highlighting here again because it is not exact replica of the uh, neurons that are present in the brain. So loosely inspired from the human neurons, human brain. That is the architecture that is inspired from the human brain. So we use a very specific architecture for building intelligent systems. That is deep learning. The main advantage with deep learning is we can deal with unstructured data as well here compared to machine learning. In machine learning, almost all of the algorithms are the algorithms that we use in machine learning. They can handle only structured data. Structured data is the data that is in the form of rows and columns, just like how you see here. There will be some columns, and the rows corresponding to that columns would be there. Data corresponding to that columns would be there. That is one thing. And another domain that is famous nowadays is generative AI, and it can be considered as sub domain in deep learning again, because it is extension of this unstructured data handling capability of deep learning, right? So here, most of the times in machine learning and deep learning, you don't generate the content, you will just predict something. For example, house price you will predict. You can predict whether the given image belongs to a cat or a dog. If it is unstructured data, and in deep learning, you do that. That is classification, image classification. And maybe you can predict audio clip belongs to a male or female. So these kind of things that you can do using deep learning. That is predictions most of the time that you will be able to do. But in generative AI, you will be able to create the content, unseen, like new content. That is what it makes different, a huge difference from AI, machine learning and deep learning in generative AI. So the again the architecture, it is inspired from the deep learning architectures, neural networks. Multiple variations are there. First, in an artificial neural network, convolutional neural networks, RNNs, LSTMs, all of these 4 5 architectures we'll discuss here. Maybe in the next 1 or 2 days we'll cover. And then comes the transformer architecture. That is why we are calling it as subdomain of generative AI. That is one thing. So you, as of now, what you need to know is what is AI and what are the things that we do in ML and what we do in deep learning and what is generative AI. That is one. Next comes the learning paradigms. In learning paradigms, we have discussed supervised, unsupervised, self-supervised, and reinforcement learning. Reinforcement learning, it is a completely different topic and it is not included here. But just to good to know what is reinforcement learning because you hear that frequently in this. So, what is supervised learning? In supervised learning, we will have both input and output labels present in the data set. That is something like you have something like this. We have area of the house, number of bedrooms, age of the building, how far it is away from the main road, and color of the building, price of the house. So all these first four, five are input features for us, and output is price of the house. This is output label, we call it as. If it is present in the data set, and if we are building a machine learning model, or if we are training model on this data set, then it is called supervised learning because we are showing the model output here well in advance during the training. That is important. During the training, if we show the output labels, then it is called supervised learning. And if there are no output labels present, we are giving the freedom to model to decide itself, then it is unsupervised learning. So use cases for unsupervised learning are, first thing that you should remember is clustering. That is, you have some uh, data points. Let us say Xcalid, I will go back to. Otherwise, I can say clustering. Yeah. Let us say you have data set, something like this, and you ask the model. This is the original data set that you had given as input to the model. And you ask the model to identify the segments or the clusters of the uh, data points that are present in this data set. So at first look, you can easily say that there is more concentration of data point that is present here. So you can make this as one group or one cluster or one segment. And then you can see there is some border that separation that is happening here in this region. That is why it is creating another group or cluster here. So that is how we are. It is like it's okay if the model comes up with only two uh, groups or two clusters, something like this, which can look something like this here. This portion as one cluster and remaining portion as one cluster, which is very, very highly likely, right? So it is okay, but we will give that like it can come up. But still we don't want to give that, okay, there are two clusters in the data set. No, we don't do that in case of unsupervised learning. That is the difference. And just looking at the data set also, you can say whether it is a supervised or unsupervised learning by looking at the data set. How? If there is no output label present, then it is unsupervised learning. That's all. Because we don't give for the training. And self-supervised learning, this is something like it is mostly used in the NLP basically, and even during the transformer training also, LLM training. So how it works is, it takes one input, which is something like any input here. Let us say this one. This is the text data that we have as input. We had decided that we will consider as training input. Then what we do in case of self-supervised learning is, first we will take one word, K means, and ask the model to predict next word. Then let us say it had predicted something is. And then we give these two as input. and then ask the model to predict an. So likewise, we progress. This is called auto regression actually, but we will discuss that terminology later on. But likewise, we progress. Like we start with one word, and then in steps or in increments, we go on. We create. That is what it is. We had only one data point, and then we are able to make like number of words minus one. That many data points will be able to create out of it. This is self-supervised learning, where we create the training data or generate the training data from the input or its own. That is what self-supervised is, and it helps us in automatic training data creation as well, because it is easy, right? You can write a logic to split it on word and then expand it by one word. And what is the output it would be? It is something like, if you want to see, if you want to see how I would prepare training data for this particular point, it is something like this. First K means this is input and this is output. Output is. And next K means is and output is al. And next K means and output is unsupervised. Something like that. Sorry, if my writing is not understandable. Let me take it. So it is something like and output is and next is this one and output is and next is and output would be unsupervised and unsupervised and output would be learning, and it goes on like this something. So this is how we prepare the training data for the in case of self-supervised learning. It is really helpful during like training of these LLMs. It helps us a lot of manual labor as well. That is important. So this is what we have discussed. And next step that we discussed is about the training of LLMs. How does the machine uh, learn continuation of that, right? So what we discussed yesterday on that point is, let me remove this at least. Yeah, we had written here, correct. So first thing is, for example, if I am working on the same use case where my target or goal is to predict the house price for a given input. These are the inputs that we have: area, number of bedrooms, age of the building, how far, color. These five input variables are there. These five features are there. Using these five features, I need to predict the house price. So what we do during the training or the model does basically is, it is something like it creates this kind of equation: C1, C2, C3, C4, coefficient 1, coefficient 2, or whatever you can. So you can say for a given C1, C2, for a given input, that is for a given area, number of bedroom, age of the building, what is the output, what is the price that it tries to predict. So then what it does basically is it substitutes here. And how does it substitute? Here unknown C1, C2, C3, C4, C5 are there, right? Coefficients basically. it is something like this. Just to make it clear, alpha 1 and some constant. For the first data point, otherwise let me write it here only. Yeah, it is 1000 and plus it is C1, not alpha, and C2 and 2 plus C3 and 7 plus C4 into 2 plus C5 into color of the building gray. So we need to identify weights to represent this kind of categorical values in the numerical format that we will discuss later. But for now, we encode it, or one hot encoding or label encoding. Multiple encoding methods are there. Let us say the value we come up with for this gray was 1. So first what we do is we substitute values like this for the first data point during the training. And for C1, C2, C3, C4, C5, we start with some random value. Like it can be 0.1, C2 would be 0.5 or 100, C4 is 1000, and C5 is 2000, something like this. We start with random values for coefficients or the parameters, we call it as these things. Parameters are weights also. So again, this in case of regression or this kind of equation building, we call this as coefficients usually in maths, right? In ML terminology, these are parameters or weights. So C1 to C5, this will be initialized randomly first and then multiplied with the inputs like how we are doing here. And then we will get some prediction from this. So let us say it was 800. So let me write here, insert below. Yeah. So here what it would be is C1 multiplied by 1000 plus C2 multiplied by 2 plus C3 multiplied by 7 plus C4 multiplied by 2 plus C5 multiplied by 2. And C1, C2, C3 are C1, C2, C3, C5 are initialized with random values. So that is what here we have written. So first step is passes all the input variable values and ask the model to predict. That is the substitution that we do. And the prediction is, let us say, 800. But actual value is 1000. Here we have it. This is the prediction. And then what we do, compare prediction value with actual value or the ground truth. And if actual minus prediction is 0, then we say that model has learned the pattern and then we will stop it. If not, then we will adjust these weights. That is where we were, yeah, I was asking this question. So, for example, there are two weights only in the original equation. That is 100 and 200 are the weights. And x1, x2 are the input variables. Usually, one more thing, we represent complete set of input variables with capital X in machine learning terminology. Capital X and output variable as small y. This is convention. Usually people follow. And when we are doing individual feature representation, you can do it with small x1 or capital X1, it doesn't matter. But if you see in any of the literature or text related to machine learning, capital X means it is input features, capital X, and small y is output feature. That is what, important. So when we have these two input variables, and multiplying are the parameters are the weights that we have are 100 and 200, and actual value that it is supposed to be 1000, but we are predicting 800. Then we need to adjust the weights now, right? Because the error is not zero here. So which one would you prefer, like adjusting 100 or adjusting 200, and why? If you gave a thought about it, like it would help. Uh, it leads to very important concept, or the very important algorithm, gradient descent algorithm, uh, for which this guy Jeffrey Hinton got Nobel Prize for. It is very simple but effective approach through which we will be able to optimize the training or the learning in machine learning models. So gradient descent algorithm, that is the starting point, starting question that he had come up with. Then he developed this algorithm. Okay. Yeah. Anyway, this one is important. Um, what I was talking about, gradient descent. So gradient descent, it which leads to back propagation, which is a very important concept in machine learning and deep learning. But yeah, first let us start with this question. Which one you would adjust, whether 100 or 200, and which is more effective? Here, the it all depends upon the error rate also. Like if you see, if you adjust the value or adjust the weight of 200, then it will have more effect on the output, right? So adjusting this value will be more effective on output prediction. So this is what is the starting point for that thinking, or the gradient descent, and ultimately to the back propagation. So that is what we do. Like what we do in case of this one is, before going to that, let me formalize few things here. This is the starting point of training. First, we initialize the weights randomly, and then ask for ask for the prediction from the model. This is first step, and then we compare it, and then we will check whether it is prediction is matching with the actual output or not. This one, as I mentioned, we call it as error or loss or cost. And if we use very, what to say, a simple error like this, which is actual minus prediction, there are chances of doing something like this. Let us say I have 10 data points, 10 data points, which look something, to make it simple, let us say only 4. So first error that came out to be -2. There are chances that, right? So original was 100 and we predicted with 102, and actual minus here error, let us say error is equal to actual minus prediction, right? And this is the actual and this is prediction. So equal to actual minus prediction. Actual minus prediction. So this is -2. And actual was 90 for another data point. And we came up with prediction of 86 and equal to same formula I can copy here also. So 4 it comes out to be. And we have another data point where we are supposed to get 99 and we came up with 1 or 2, and here the error would be -3. So now we have a data point where we are supposed to get 80, but we came up with 79 as prediction, then error would be 1. So now if you calculate total error, if you select this and sum comes out to be 0. So then ultimately the total error that you get, it is 0. In that case, do you think that this model is performing really well? But still there were some issues, right? So these kind of issues will come if we use the simple error calculation, which looks something like this: actual minus prediction. This is okay, overall error. So what we do usually is, and also one more scenario, like for example, if you are working on logistic regression or this classification use case, where we need to say something like this: for a given input, we need to say output label here is predicting house price, right? Rather than predicting house price, what if you have to come up with something like this: customer will buy or not buy, otherwise will buy, will not buy. Looking at these features, customer will buy or not. If this is what is the use case is about, then we call it as classification use case. Basically, we need to classify for a given area of the house, number of bedrooms, age of the building, how far it is from the main road, and the color of the building. Then we need to classify whether somebody is going to buy it or not. Then this is classification use case, we call it as. Again repeating, for a given input parameters set, if the output is numerical value, then we are going to predict the numerical value. That is called regression. And for the given input set of parameters, if the output value is categorical, something like this, which looks something like this, then we need to predict to which category this given set of input parameters belongs to. That is called classification. So you have two images with you. Sorry, you have an image with you. You need to predict whether it is a cat or dog. Then it is classification. You are classifying the given input data. For a given input, for a given input parameter set, which looks something like this. Um, in the first session that we discussed, right? How long customer stayed with you, and months of inactivity, and what is the monthly bill that he is generating, and what is the number of complaints, what are the number of complaints he had raised. And we need to predict whether he is going to churn or not, in the sense he is going to leave the company or not, leave the service or not. then it is classification use case. So these are two important categories of the problem statement that we work with in machine learning. For that matter, even the self-supervised learning or the LLMs that we train upon ChatGPT or Gemini or Llama, cloud models, anything, those are also comes under classification models. How it is something like what they do usually, these models, you give something prompt like what is capital of India. Let me write enter it here. That is better. What is capital of India? If this is the prompt that you had given, what it does is capital of India is New Delhi. It comes up with answer something like this, right? So here what it does is it takes this one, two, three, four, five words as input and tries to predict next word. So in that process, what it does is if it has something like it obviously understands that this is English, or let us say it is a dumb model, it doesn't know anything, but it has to predict something. So what we do is usually it has some vocabulary actually. It doesn't create any random text after this word. It doesn't create like that. How it works is it has some vocabulary that is something like there is a imagine there is a hypothetical language where we have only 10 words. Like first one, just to make it simple, I am taking it as capital, and another one is W2, W3, W4 till W10. This is the vocabulary of that language, that hypothetical language, where you have asked the question. Then what it does is when it receives this input, what is capital of India, then to get this next word, it goes to its vocabulary, it checks its vocabulary, and then find out which is the most probable next word. Next word prediction is what it does. NWP. Next word prediction it does. So here what it is classifying is basically what is next word. In that process, it classifies the words into two categories. One is next word or not next word. That is what it happens in the back end actually. So once it predicts this next word, capital, then goes and checks its vocabulary again and divides it into the segments, or the classifies this into segments. If, for example, if it was off here, then it does the same classification again. Like if this is what is the second word in the vocabulary, hypothetical vocabulary that it had, then it does the same thing. What it does, these remaining words, let me highlight in different color. These words are not the next words. And this is the word that is it predicts or selects as next word. That is why it comes here. So what it is doing literally here, it is classifying the vocabulary as next word, classifying the vocabulary as next word or not next word. So that is why we talk always about regression classification. Regression classification. Any other problem statement can be like interpreted as classification or regression. There are like clustering, segmentation, like how we discussed here. Segmentation, topic modeling, anomaly detection, all of them we can, just for the namesake you can have, but all of them are classification models if you look at it. What is segmentation? In topic segmentation, what we do? We create the segments of the customers or create the segments of topics or the text, whatever. So that is also classification. What is topic modeling? Topic modeling is nothing but identifying the number of topics or the themes that are present in the data. So that is kind of classification. But there are different techniques or the methodologies. That is why, and one more major difference in terms of this topic modeling or segmentation or whatever that comes here. These are also unsupervised. So, but classification is supervised. That is one important thing that you need to remember. Otherwise, you will get confused again. So classification, that is whether identifying and given image is cat or dog, it is supervised learning. Whereas clustering, topic modeling, segmentation, anomaly detection, all of these are unsupervised learning. Output label may not be present in the data set, in the training data set. That is why. So let us come back here. So we are discussing about the training process. If you are wondering what we are doing right now. So we have this input and then predict the output and then calculate this error. So in case of classification, what would be the error function that you would come up with? For example, let us say I have this as X and output is Y. I have only one feature, so that is why I am writing 100, and it is a cat, and 200, it is a dog, and 150, it is a dog, and 70, it is a cat. Just it is some input feature. Let us say it is the weight, it is representing weight or something. So if the weight is less than 100, less than or equal to 100, then I am saying a cat. If the weight is more than 100, then I am calling it as dog. If that is the pattern that I had followed while creating the data, or that is the underlying pattern that is present in the data, then that is fine. That is the rule that our model has to come up with. But ultimately, when it is predicting, let us say this is widespread, that is prediction, and it predicts as dog. So how would you calculate the loss function here? Something like this, loss or error. For that, we use something called as cross entropy loss function. We will discuss about it. So this, what I want to mention or highlight here is this error function, actual minus prediction. It may not work always. So we use different loss functions here in ML. One more issue with this actual minus prediction, this simple actual minus prediction error function or loss function is something like here we do y minus y pred, which is not differentiable at all. It is not so smooth at origin. When we draw the loss function, there is a huge what to say emphasis in machine learning for the smooth functions, which looks something like if anywhere for any purpose, if there is a function which looks something like this, I would prefer this rather than this, where there are abrupt edges changes, or we call it as cusp is there. I don't prefer this in machine learning because it involves a lot of differentiation or calculus in the back end when we are calculating these errors and even back propagation training. During the training, we do that. So we prefer this kind of smooth functions. The transition should be smooth, not abrupt. And this one that you see here, y minus y pred or actual minus pred, that is something like this actually. If you are wondering what is there on x-axis and y-axis, it is same. Error is the y-axis, and on x-axis it would be what is variable here. Variable is prediction, right? Actual is constant. Prediction is variable. So on the x-axis it would be y pred, and the dependent is error function. That is error high here. So as the prediction approaches actual value, that is where this becomes zero. Otherwise, if you want to draw it properly, I can draw that as well. If I have to draw this y minus y pred on the graph, how I would do is like this. This is the error function on y-axis, and the variable is here is y pred on x-axis, right? Usually on the x-axis it would be variable, and on the y-axis it is dependent. So dependency is there for this error on which independent variable or which is y pred. So as it is y pred is approaching y, a constant value. Let us say this y is some 10. So that 10 is here. At this point, it is 0. Error is 0. So I am writing, uh, this point would be on the x-axis. And as y pred increases, that is in this direction, then error, what happens to error? This is 10. It is already 10 here. And on this side, error goes to negative, and that too in the linear fashion, something like this. And it should be increasing, which is in this direction, right? And as the y pred decreases, that is becoming less than this 10 value. Let me write it here so that it will be clear. And then error term, what happens to the error? It reduces. That is this point. So it may look something like this, Mikey, if I am doing it correctly. So which is like this. This sharp edge is there. That is the issue. So we don't prefer this kind of loss functions in machine learning. That is why what people have done intelligently here is, rather than doing this, let us do this y minus y pred whole squared. This is a parabola, right? This is something like x minus 2 whole square. It is a parabola. If you want to see that diagram, uh, forget that website name. Maybe I will show you tomorrow. That is why you understood, right? What is the requirement for different loss function in even in case of simple regression? We don't prefer smooth functions because of they are not differentiable at that cusp. If you remember it from your calculus classes, this function that you see here, it is not differentiable at this particular point. Why? Why? Because we don't know what is the change here. What is the differentiable meaning? Differentiable is LT is nothing but how much change in y value it will cause, or how much this function changes at this point if I change the independent variable by some unit. So there is no it is not defined here at this point. At this point, I can say it will be like this, or it will the slope is there, but here there is no slope. So slope is the one that tells us this point, right? How much it would change, how much the function value will change if I change something. So because here we have some slope, here at this point we don't have. That is why it is not differentiable at that point. It's okay. So we have something called loss function. So ultimately what we try to do is we try to reduce this loss function. That is this y minus y pred that we decided earlier, that we will use this. y minus y pred whole square. If this is the loss function, we decided loss function is equal to this one. And ultimately, we should try to reduce this one. How do we reduce this is the question. Programmatically, we have to do it. How do we do? Usually for a given function, what we do to identify the minimum value dou L by dou Y pred. Because why I am writing dou Y pred here? Because it is the dependent variable, dou L by dou Y pred. So we do differentiation 2 times of Y minus Y pred and then calculate what is the Y pred value, something like that. Equal to 0 we do, right? But this is also not so correct because there are high chances that we will get stuck in the local minima, right? And this last function that we see, this y minus y pred is very simple. But as the number of parameters gets complex, this also will get complex. So for that, we have something called as gradient descent. So first thing that I want to repeat again here is what happens during the training is we have the inputs, we initialize random weights or the parameters like this and substitute them and get the prediction. Once we have the prediction, then we compare it with the ground truth value or the actual value and get the error rate. And then we substitute that values. Basically, we to calculate the error, that is fine. But if in case if we decide that we are not going ahead with the error, simple error, actual minus prediction, then we need to calculate the loss or the cost function. That is y minus y pred whole square. For this particular scenario, it is error square actually. That's all. But there would be some other different loss function that we will come across for different algorithms or different use cases. That is why I am trying to make it generic. So once you receive this prediction, then next step is substitute it in the loss function to get the total loss that we have. So let us say we have total loss of 1000. Then we should try to reduce it to 0, closer to 0, right? That is what is our ultimate goal is. How do we do that? By adjusting the weights. How do we adjust the weights? That is the important thing. How do we adjust the weights? Is using gradient descent. If you get some time, try to go through theory once, what is gradient descent during your, maybe tomorrow you don't have a session. So it is very important algorithm. That is why I want to spend some time upon. Till this point, is it clear what is training? First one is we have the inputs and we initialize random weight, substitute it, and then get the prediction. That is the ultimate goal here in the first step. Once we have the prediction, then we substitute it in the loss function and get the total loss. And ultimately, we should try to reduce that loss as much as possible, if possible, to 0. And how do we do that? Is by adjusting the weights. But how do we adjust the weights? That is done through gradient descent. This thing I want you to have it like printed in the mind. Training process is something like this. So that gradient descent, what is gradient descent? How does it help us adjusting weights? All those things we'll discuss next. You have any questions still? I'm going a little bit slow because you have to get habituated of this terminology first. Uh, yeah. Any questions still? No? At least you are able to understand, right? Please confirm that at least.
Yes, Nageshwar, it's going on. Like it's on the track. So day by day, we will get into the terminology. Became familiar and easy for us.
Yeah. I don't want to discuss too much of the mathematics part as well. Just intuition is enough. because we are not focusing too much on the machine learning. We want to reach that level where you will understand the terminology and then generative AI in depth. That is what is the goal, right? So I will not get into too much of the mathematics as well. Uh, if you understand the concept, that is enough for now. Yeah. If no questions, then we will drop off. We will meet on Monday. Okay.